In this meeting, we're going to be discussing section 5.2, which deals with graphing of polynomial functions and their models. What we're going to be doing is analyzing everything you learned in the previous section in 5.1, which was all the details about the graph of a polynomial function, and now we're going to put all those details together. I've listed a 5-step process in order to be able to help you in creating these graphs by hand. Step 1, always find the end behavior by finding the power function that the graph resembles. In other words, look at the degree. This particular example here has a total degree of 5. You see that because we have, if we were to multiply all of this out, unfoil and get rid of and distribute all of the parentheses, you're going to end up with a total of 5 x's as the highest degree to start with. Notice you have an x to the third here, another single x here, and another single x here. And when all of this would be theoretically multiplied out, you notice that the very first term is going to be x to the 5th power, which means this polynomial would have a degree of 5. When it has a degree of 5, that means the end behavior of this graph is going to have the end behavior of an odd exponent. And if you recall back from the previous section, a simple graph of that, an odd function is going to have the end behavior of something that looks like this. Remember, odd exponents start from the bottom quadrant 3 and continue up. They might do some changes and turning points in the middle, and will end up in the first quadrant, going up forever to the domain of positive infinity and range of positive infinity. If it were an even degree, then it would be up, up. Once we know what the end behavior will look like, the next step says, now find the intercepts. So let's go to step 2 and find the intercepts. Remember, when you find the intercepts, you always plug in the opposite letter for 0. So for example, if I want to find the x-intercepts, we substitute y is 0. So for this one, we'll substitute y is 0. Remember, f of x is the same thing as y. So we say 0 equals x to the 3rd power times x minus 1 times x plus 3. Since all of this equals 0, using the 0 product property, we state each of these factors could be also 0. So I set each of those 3 factors equal to 0. And solve for x. So that means x could be 0, 1, or -3. So those will be my x-intercepts. So I'm going to go ahead and graph those on my graph over here. I'm going to have points at 0, 1, and -3. Zero, 1, and -3. Now from there, we're also going to find our y-intercepts. Our y-intercepts we find by setting the opposite letter equal to 0. So if we plug x is 0 into all of these positions, we're going to have y equals 0 to the 3rd power times 0 minus 1 times 0 plus 3. So y equals 0 times -1 times 3, and 0 times -1 times 3 is in fact 0. So I will have a y-intercept at 0. But I already have that point there since it was the origin. All right, now that we have found the degree, which indicates the end behavior, we have also found the intercepts. The next step then is to determine whether the graph of f crosses or touches the x-axis at each of those intercepts. So you're going to need to factor the polynomial, which in this case it already is, and then look at the multiplicities. So in step 3, let's analyze each of these zeros. Since we know we have a 0, let's look at the first one. Let's look at this 0 right here, which would be the 0, 0. It has a multiplicity of 3. The multiplicity of 3. See, this 0 has a multiplicity of 3, which is an odd number, which means on the graph, it will cross through and venture to the other side. When I look at the next 0, and this 0 would be the number 1, it has an exponent of 1. So this 0, 1 has a multiplicity of 1. And since the exponent multiplicity is odd, it will also cross the graph at that x-intercept. The last 0 is at -3, and it has a multiplicity of 1, which is also odd, so it will also cross at that location. So at this point, we can do some more digging onto our graph. Since we know that the end behavior started from the bottom, we know it's going to come up and eventually touch this 0 at -3. And at -3, the graph will cross through this point to the other side. Now, I don't know the height of what this is going to do, but at some point, whether it's way up here or takes a shallow dive, it will eventually come back down to touch this 0 here at the number 0. And at the 0, 0, it will again cross through that 0 to the other side. Now, again, I don't know how deep this graph will go, or if it will just be a shallow change, but it will eventually come back up and touch this 0, and it's going to have to cross through to the other side because we know eventually it's going to have to meet this end behavior on the other side. So to find out what those peaks and valleys are, the best bet would be to find other points on the graph. Okay. First, let's look at the determining what is the maximum number of turning points on the graph. For this, the maximum number of turning points is n-1. So we're going to write the maximum number of turning points is the degree. In this case, the degree is 5. So it's going to be 5 minus 1, which is 4. And lastly, the last step says, put all the information together to graph it, and then make one additional table of additional points if necessary, which in this case, I think it would be. I'd like to find a couple more points in here, maybe when x is -1 and -2, and maybe one more right in here at 1/2 to see how deep this peak, or shall I say valley, is. So I'm going to do just a couple more points just to see exactly what this graph is doing. So I'm going to use my calculator, and I'm going to come up with those answers. So when I put these values into my calculator, -2 for x gives me a y value of 24. An x value of -1 gives me a y value of 4. And an x value of 1/2 gives me an approximate value of about -0.2. I'm just getting an approximation so I know where to plot those points on my graph. So up here on my graph, again, let's plot the point -2, 24. So that point is going to be way up here on my graph, something really, really, really high. Okay, so we'll call this 24 up here. Then we're going to have another point at -1, 4. So -1, 4 will be down here. So at this point, I could connect my dots. I know how tall this graph is going to be. Something like that. Then at some point, it's going to turn direction. I do know that I have one other point located at 1/2 -0.2. So it's going to be a really shallow valley like this, and it will turn around and skip the other direction. Just to prove that we got the graph correct, I also ran this graph through a graphing technology, either on a graphing calculator, or you can use desmos.com. They also have a nice graphing calculator use as well. And you can see that this graph does indeed look a lot like the graph that we created here on my sheet. You can see that if I blow it up, it does seem to have the maximum of 4 turning points. It looks like we got 1 turning point at the top, 1 down here at the bottom, that's 2, 3, 4 turning points. And also we have our 3 zeros here at -3, 0, and 1. Okay, let's try another one. On the next page, I have 2 more examples. Here I've got another polynomial. We're going to follow the exact same steps that we had on the first page. Remember, the first step says to find the end behavior. So let's first look for what the end behavior would be. The end behavior is going to mimic the degree of this polynomial. This polynomial has a degree of 1, 2, 3, 4. So this has an end behavior similar to x to the 4th as the power function, because it has a total degree of 4. Let's also find in the second step what the intercepts will be. Recall the x-intercepts are found by substituting y in for 0. So if I substituted y is 0, I get x plus 2 squared times x minus 2 times x plus 4, which indicates one of these 3 parts using the 0 product property must also be 0. So that means x-intercepts will be at -2, 2, and -4. Let's also find the y-intercepts. The y-intercepts are going to be found by substituting x is 0. So I get y equals 0 plus 2 squared, 0 minus 2 times 0 plus 4, which is going to be equal to 4 times -2 times 4, which obviously gives us -32. So we'll have a y-intercept at -32. Let's go ahead and find the rest of the information, then we'll put it on the graph last. The next step we're going to do is in step 3, we're going to determine whether the graph crosses or touches at each of those x-intercepts. So let's look at each individual 0 and decide whether the multiplicity tells us what it's going to do on the graph. Well, as you can see, we have 3 zeros at -2, 2, and 4. At the 0, -2, you can see it has a 2 exponent, which is even. Since it has an even multiplicity, that means the graph will touch in reverse direction. At the 0 of 2, it has a 1 for its multiplicity, which is odd, therefore it will cross through to the other side. And finally, the 0 of 4, oh, excuse me, that should be -4, shouldn't it? The 0 of -4 it should have a multiplicity of 1, and therefore it is odd, which means it will also cross through. The last thing we need to do in step 4 is also find the maximum number of turning points. So up here, let's find the maximum number of turning points possible. N minus 1. Since the total degree is 4, I could have a maximum of 3 turning points. I should write maximum number of turning points there. And then step 5, we're going to find a couple of extra points as needed. So let's go ahead and graph what we have, and then we'll decide what extra points we may need in order to create a good graph. So let's look at the end behavior. The end behavior is going to look similar to the power function x to the 4th power, which means it will be up, up. Then let's look down here and let's find our zeros. Our zeros are going to be located at -2, 2, and -4. So let's plot those here. Now at each of those zeros, we know what it's going to do. At the 0, -4, it's going to cross through to the other side. So this graph is going to come down to this 0, and it's going to cross through to the other side. At the 0, -2, it's going to touch. So at some point, this will reverse direction, come back up, and it will simply touch and reverse. It will not cross through to the other side. It will just touch and reverse. At the 0, 2, it will cross. So at some point, this will continue down, come back up, and it will cross through to the other side because we know it eventually is going to have to meet the end behavior on the other side. We don't know the depths of these valleys in here. We do know one other point because we know the y-intercept is way down here at -32. So if I make this a little bit bigger, way down here at -32, I actually know there will be a point on my graph. So I do think it would be advantageous to find where this point right here, maybe -3, -1, and 1 will put us in those valleys. So those are the 3 points I'm going to find at -3, -1, and 1. And then we can put those on our graph. If I plug -3 into this function right here, I get -3 plus 1, which is -1 squared, which is 1. -3 minus 2 is -5, so I have -5 times 1, which gives me -5. Then I'll have a point at -1, so I'll put that in. That gives me 1 squared, which is 1. -1 minus 2 is -3. And -3 times 3 is -9. And then also another point at 1, which is going to be 3 squared, which is 9. 9 times -1 is -9. -9 times 5 is -45. So that point will be way down here. So it looks like my graph is going to do something like this. Like that. So I'm going to put that into Desmos, and let's see if that is similar to what technology will give us. As you can see, the Desmos does have a very similar graph to what my sketch has. You can see that it has definitely the 3 zeros at -4, -2, and 2, crossing through the -4, touching at the -2, and again crossing at 2. And it does seem to have a really large valley going all the way down to -40 something here. So my sketch is not too far off from what technology gives it in a more accurate template. Okay, let's try one last one. Here I've got a polynomial. This time it is not in factored form, okay? So this time we're going to have to factor it, because the only way we'll be able to determine where those zeros are is if we factor it first. So that's actually not one of the steps in the analysis of the graph, but it's always recommended you factor it first. Since this has 4 full terms, the first thing you always look for is to see whether it has a greatest common factor first. In this case, the greatest common factor is 2x. So I'm going to take a 2x out from all 4 terms, which leaves me with x to the third plus 6x squared minus 8x minus 24. Once I'm done there, and you still have 4 terms left over, the only way to group 4 terms is to group. So I'm going to try to group the terms inside. These 2 terms have an x squared, an x squared in common, which leaves me with an x plus 6 left over. These 2 terms have a negative 8 in common. I knew I did something wrong there. When I take that 2x out, shame on me. This should have been reduced down to a 4. My apologies there. So that means I can take a negative 4 out instead, right? So I'm going to take the negative 4 out. That leaves me with x plus 6 inside. I knew I was doing something wrong because remember, when you group, you always have to have these 2 sets of parentheses match. Otherwise, there is no grouping to be had. So that's going to leave me with, we have the x plus 6 in common. And then what's left over is the x squared minus 4. Hey, actually, I'm not done. This is the difference of squares, which can be factored even more fully. So it turns out that this was factored all the way down to its smallest possible factors. Once we have it there, then we are able to complete our 5 steps. So our first step is to, I need an extra piece of paper there. Our first step is to determine the total degree. So in this case, the total degree is going to be, I have a single, well, it's actually pretty obvious from the beginning. It's a degree of 4, but also I can see here I have 1x plus another plus another plus another. So it's going to equal a total of a degree of 4. So the end behavior of my graph will be to the 4th degree, which indicates on a graph that this is going to be, again, another up, up type of an end result. The second step then is to determine your intercepts. Okay, so let's look first at my x-intercepts by substituting y is 0. So when I do that, I substitute if y is 0, we say this was the original function. So 0 equals 2x times x plus 6, x plus 2, x minus 2, which obviously then means x can be 0, negative 6, negative 2, or 2. So there's actually 4 x-intercepts. After that, we're also going to find the y-intercepts. The y-intercepts are found by substituting x equals 0 back into the original function. So that means y equals 2 times 0 times 0 plus 6 times 0 plus 2 times 0 minus 2, which is 0 times 6 times 2 times negative 2, which in fact is 0. Let's keep going. After we know that, the next step is to find the find out where these zeros are crossing and touching. So let's go back here and let's list all of our zeros, what the multiplicity of each of those are, and then also what it is doing on my graph. So I have zeros at 0, -6, -2, and +2. You can see in the graph, they each have a multiplicity of 1. They're all to the first power. Since those are all odd, that means they will cross at each of those locations. The fourth step is to determine the maximum number of turning points. The maximum number of turning points is found by taking the degree minus 1. In this case, the degree is 4, which means I'll have a maximum number of turning points of 3. Our last step is to find a few extra points in a table necessary in order to make the graph. So let's list what we have. We know that the x-intercepts are going to have the following points. So we're going to have zeros at 0, -6, -2, and 2. We'll also have a y-intercept at 0, well, that's already located here at the origin. I know that this graph is going to have an end behavior that starts in the upper second quadrant and will come down and hit that very first 0. And at that first 0 at -6, you can see it is going to cross through to the other side. At some point, it will reverse direction, come back up and hit this 0 at -2, where it will cross through to the other side. At some point, it will reverse direction, come back and hit this 0 at 0, where it will cross through to the other side. And then at some point, it will reverse direction, where it will come back and hit this 0 at 2, and it will cross through to the other side. And then finally meeting the upper end behavior in the upper right-hand quadrant. The only thing I don't know are the local minimums and the local maximums for where this graph is hitting. So that's why I'm going to find just a couple extra points, maybe at -2, -1, and 1. So let's find here at -4, -1, and 1, and find out where that takes my graph. So I don't have enough room. Let's put this down here so I can see it. Right here. Okay. So here we go. I'm going to try -4. That's going to give me 2 times -4 is -8 times -4 plus 6 is 2. -4 plus 2 is -2, and -4 minus 2 is -6. And when I multiply all of those straight across, I'm going to cheat and use my calculator. I get -16 times 12, which is -192. So it's really, really, really far down. Let's try another one at -1. 2 times -1 is -2. -1 plus 6 is 5. -1 plus 2 is 1. And -1 minus 2 is -3. And that's going to give me -10 times -3, which is 30. One more here. Let's try 1. We'll have 2 times 7 times 3 times -1. That's going to give me 14 times -3, which gives me -42. So they're going to be quite far off my graph, but when I come up here to try to put those on, at least I know that this graph is very, very long, meaning at -4, it's going to have a point way, way down here at -192. So it's going to be a very long graph. Then up here at -1, it's going to go up all the way to 30. And then down here at +1, it's going to go all the way down to -42. So this just gives you an idea of what the graph looks like. It's actually probably going to be a lot longer and skinnier than that graph I have drawn there. And I'll show you that and confirm that in technology now. So you can see using technology that I do get the exact same graph. It does appear to be a little more compressed from the left and right direction. But it does have these same zeros at -6. I can zoom that in just to verify that. You can see at -6, -2, 0, and 2. It does seem to go down, up, down, up. And if I zoom back out, you'll see that it does seem to go all the way down to negative almost 200 and some. So it's a quite lengthy graph, but it does seem to match our graph over here on the right-hand side.